Hey everyone! In this video I'm going to review some of the basic properties of sound waves, and in particular I'll discuss different descriptions of them in terms of pressure variation, density variation, or displacement of average particle location. I'll also discuss the phenomenon of beats and the Doppler effect. So first, what are sound waves? Well, we're all very familiar with sound waves right now. You are hearing my voice because of sound waves, but these in particular are longitudinal waves, and they have a particular velocity. So with where here B is the bulk modulus and rho is the density. So as with all waves, the velocity of the wave just depends on particular properties of the material at which it's moving through. So the bulk modulus is a property of the material that sort of tells you about its stiffness. And then, of course, you're all familiar with what the density of a material is. So sound waves are longitudinal waves. Again, that means that their displacement is along the direction of propagation. So this is sort of like the way a wave down a slinky moves, and they have this particular velocity. So everything that I'm going to discuss in this video, I should also add, is in one dimension. So let's consider a pipe, and then we have some source over here. So this is some source, and what we're going to do is we're going to send a sound wave, a sinusoidal sound wave, down this pipe. So what I'll do is I'll sort of roughly represent areas of high density of air molecules in this way. So this is sort of a high density region. So we're sending a sinusoidal sound wave, and so with some particular period, we'll have many copies of these high density regions, right? And so we could plot this so what I'm plotting is again, so this is all at fixed time. Maybe I'll write that in a different color. So at fixed time. So we're really considering some time snapshot of what our sound wave in this one-dimensional pipe looks like. So we can plot the change in density by just sort of looking at the way I roughly drew it. We're going to imagine that this is some sinusoidal sound wave. So we see here we have areas of high density or higher than normal density. So of course this is the change in density. So this is measured relative to sort of the density of the air in the room, say, or the air in the pipe before the sound wave was sent through. And so what we have is something, I didn't draw this perfectly. Oh, that's terrible. It's a terrible looking plot. Well, maybe you get the idea, maybe not. Sorry, let me draw this lower one more time. So these are all high density. And what that means is that right in between we must have lower than normal density. Okay, this is going to look better now. Where it was just a much shorter wavelength wave than I initially imagined. So again, this is location, and this is the change in density. And then of course it would continue. And you can show that, so this is the density, and I mentioned that there are multiple ways you can describe a sound wave. So the next is in terms of pressure variations. And so let's see, I'm going to draw two more plots here. I'll make sure I have enough room, which it looks like I do. So you can derive the relationship of this change in density to the change in pressure of the air, which I'm not going to derive right now, but this is equal to the change in pressure is equal to the change in the density times the bulk modulus divided by the baseline density, which maybe I'll call rho naught. And so what I see is that if the change in the density is sinusoidal, then the change in pressure is also going to be sinusoidal. And everything is going to match, but because we have this constant factor, then the amplitude of this might be a little different. So let's say maybe it's smaller. Could be smaller or bigger, it depends on the particular constants, what B and rho naught are. So this might look like this. Where what you should really note is that the maximum change in pressure, so this is density rho here, and this is pressure. Don't get confused between P and rho. So what we see is that all of the pressure maximums occur at the exact same place as the density maximums. And then the minimums are at the same locations as the density minimums. But on the other hand, we might want to plot the displacement, so the average particle displacement, air molecule displacement, which is often denoted by the letter S. And you can similarly derive that the change in pressure is related to now the derivative of the displacement. And what that means is that if this is some sine function, so the derivative of sine is cosine and vice versa, or the derivative of cosine is negative sine. You've got to remember that sine. So what that means is that before, where we had these maximums, this now is where the displacement is going to vanish. So it should vanish actually like this. Right. So what you see is that the displacement curve is offset by 90 degrees from the density and pressure curves. And what that means is where you have, when you consider, for instance, harmonics of sound waves, where you have pressure nodes, you have displacement antinodes. And when you have displacement nodes, you have pressure antinodes. So when you consider harmonics of sound waves, standing sound waves, the nodes and antinodes are flipped for pressure and displacement, exactly because this shift here. So these are sort of the general ways you can describe sound waves. So now let's discuss just a couple basic properties, or I guess not properties, but special phenomenon. So the first is beats. Now this occurs when, when two waves are superposed. At the same location, with different frequencies. Let's call that F1 and F2 of our two waves that we're superposing. And it turns out that you end up with this interesting phenomenon where maybe I'll plan ahead a little bit and then describe this pink curve in a second, So when you do this, the net result ends up being a wave that looks kind of like this. Oh, that one was a little funky, but you get the idea. So basically what you have here is you have a sinusoidal wave, but what it has is its amplitude is varying. So, so this might be in space. Or I guess I'll use S because that's what I've been using, the displacement. So you have an oscillating amplitude. So what this really means is when you're listening to two waves that are superposed that have slightly different frequencies, what you're going to hear is sort of a wah, wah, wah noise. And what that really is that's because the amplitude is related to the loudness of the sound. You're really hearing this oscillating amplitude of your sound wave. And you could compute the magnitude of this, the frequency of this oscillation. So the frequency of your beats, you would say. And this is just the absolute value of the two frequencies that you have, of the difference of the two frequencies. And so that's basically all there is to beats. And then the final interesting phenomenon that you talk about a lot is the Doppler effect. And this is the effect when you have, when you are either moving towards or away a source of sound, or the source itself is moving towards you or away from you. And what you hear is you hear a shift in the frequency of the sound wave. And you could compute that to be, so the f prime, which is the observed frequency, is equal to the emitted frequency of the sound wave times, so I'll fill a couple things in a second. So what all of these things are so this is the observer speed. This is the source speed, where these are constant values. Oh, I guess the V without a subscript is the speed of sound. So that's going to depend on the medium through which it's traveling. So if it's just traveling through air, then it's the speed of sound in air. And then you'll notice that I have these interesting signs. And this is just a way of writing it where, so you could define V sub observer and V sub source as positive quantities. And then either the frequency will increase if the source and the observer are moving towards each other. The frequency will decrease if they're moving away, so it'll hear higher pitched. So when a train is coming towards you, it hears higher pitched, but then when the train passes you and moves away, then it's lower pitched. And so basically in those different circumstances, you have to use the plus or the minus sign. So the ones that I wrote in blue here are for towards each other. So this is for either the observer moving towards the source or the source moving towards the observer. And then the bottom ones are away from each other. So you have to be very careful about these signs, but basically if you just remember the fact that the observed frequency should increase if they're moving towards each other, and it should decrease if they're moving away, then you should always be able to get the answer right. All right, so those are some basic properties of sound waves and some special phenomenon involving sound waves. So thanks.